好，那我们开始这周的理论物理报告吧。这周我们很开心请到了密歇根大学的孙凯教授，然后他今天的报告题目已经在这，大家可能看见了。然后我先简单介绍一下孙老师。孙老师是09年从 UIUC 拿到博士学位，然后后来加入马里兰大学做博后，然后12年加入密歇根大学成为 faculty，然后现在是 named as a Slogan Research Fellow in 2015年。然后它主要是 how the display between particles in complex system give rise to emergent phenomena and distinct phase of matter。它在理论赛很多基础物理的问题中取得很多很优秀的成果，所以我们欢迎孙老师吧。好，孙老师您开始吧。
好的，谢谢。Okay, great. Thank you very much for the introduction, and it's my great pleasure to be here. And thank you all for coming. I'm very grateful that I have this opportunity to discuss some of our recent work about infinite hyperbolic lattices. Let me first thank my collaborators, Nan and Francesco, James, Zab, and Xiaoming. And in particular, I want to highlight Nan Cheng. So he did all the hard works and made a critical contribution to this project. And in addition, similar to many of the students in the audience, Nan is also alumni from Fudan University. He was an undergraduate student at Fudan University, graduated about 4 years ago. He is brilliant, and I think he's a very good example of outstanding students nurtured by Fudan University. Okay, so in today's talk, I will mainly focus on what interesting physics will emerge if we put two ingredients together. One is curved space, another is lattices. So curved space is actually is something that emerged in many different sub-branches of physics. For example, it emerged in gravity theory of general relativity. It emerged also in the study of ADS-CFT. It also plays a very important role in many topological field theory, for example, the Wenzel coupling between Chern-Simons gauge theory and the gravity fluctuations. Lattices is also something that we see a lot in physics. It emerged in all crystals, and it can be utilized to regularize quantum field theory. And the rich symmetry structure of lattices also gave us many interesting new physics, such as topological crystalline insulator, symmetry indicator theory, topological quantum chemistry, and fragile topological insulator, etc. Okay. And when we put these two ingredients together, actually lots of interesting physics will emerge. In the last few years, there has been lots of studies about the interplay between curved spaces and the lattices, and many interesting phenomena has been discovered. So to motivate today's talk, let me mention one more example about how curved space lattices can help us understand the interesting physics. Let's consider packing of polyhedrons. So assume we have lots of polyhedrons, and then we put them together, lots of identical polyhedrons, and we put them together, and we want to ask what will happen. Okay, among all the 5 regular convex polyhedrons we have, this problem happens. We only know the answer for one of them. We only know the answer for cubic. Okay. So if we have lots of cubics together and we pack them together, we know what will happen. The system will form a cubic lattice. This is because cube can be perfectly packed and densely packed in 3D space. All other polyhedrons, if we want to pack them, we don't really know what will happen. Okay, and the reason is because actually this is a so-called geometric frustration. For example, if we try to pack a tetrahedron, no matter how hard we try, we can't get close packing. There will always be some gaps. And for this tetrahedron, if we glue it to the neighbor on the left-hand side, the right side will have a gap. If we glue it to the neighbor on the left-hand side, the right side will have a gap. No matter what we do, this tetrahedron cannot be happy. No matter which side we glue it to, there will be a wrong side with one of its neighbors. And this physics is very similar to the geometric frustration in frustrated magnets, where the spin don't know whether it want to point up or down. And the geometric frustration in frustrated magnets gave us lots of interesting physics, like highly degenerate ground states and the emergence of quantum spinning liquid states. And for the packing, this geometric frustration gave us very similar complications. We have, again, lots of nearly degenerate or degenerate ground states, and systems don't really know what to do, how to minimize its energy. Okay. And although this is a very complicated problem, we don't know much answer, but if we go beyond the Euclidean space and go to a curved space, turns out this problem become extremely simple, can be extremely simplified. For example, I mentioned earlier on tetrahedron cannot be packed in flat space, but if we go to a curved space, a 3D surface of a 4D sphere S3, then we can have very nice and perfectly packed tetrahedrons. And this structure is known as the 600 cell structure. This 600 cell structure basically has 600 tetrahedrons. They perfectly pack with each other on the surface of a 4D sphere on S3. And they form a periodic lattice in this curved space, and it's fully packed. It has a unique ground state, and we know exactly what the packing structure is. Okay. And we can perform a duality transformation and get the dual lattice. The dual lattice is the so-called 120 cell structure. And 120 cell give us a perfect packing for dodecahedron. Okay, so this packing in flat space is very difficult, but if we go to curved space, we get the periodic lattice. It's become very easy. We know exactly what is the ground state. But of course, our universe is in flat space. We can't stay in curved space. Eventually we need to go back to flat space. So what we could do is we could start this perfect packing in curved space, where we find the exact ground state. And then we flatten this curved space structure back to our 3D Euclidean space. We know that when we try to flatten a curved structure into a flat space, this flatten will introduce stress, and this stress will introduce energy cost. And we can calculate this energy cost and try to minimize this energy cost. And minimizing this energy cost will tell us what structure is favored in our Euclidean space. And we perform this analysis for tetrahedrons, and we find some very interesting packing structures. Most interestingly, these helicoid structures. Okay, and these helicoid structures is actually quite unexpected here, because tetrahedron is achiral. Tetrahedron, if we take mirror image, it's the same tetrahedron. And this packing structure, this 600 cell packing, is also achiral. If you take mirror picture, it's exactly the same as itself. But when we try to flatten the structure into flat space, the system turns to spontaneously break the chiral symmetry. And the system will choose whether it wants to form a left-handed helicoid or right-handed helicoid. And we further compared this theoretical prediction with experiments. This experiment basically is a nanoparticle self-assembly of tetrahedrons, and the agreement is very nice. It agrees qualitatively and also very good agreement at quantitative level. Okay. And this principle of going to curved space and then back to flat space actually applies generically for all regular polyhedrons. For almost all of these polyhedrons, we can pack them in curved space. For example, these structures can be packed in 3 sphere. And one special example is icosahedron. Icosahedron cannot be packed in 3 sphere, but it can be packed in 3D hyperbolic surface, H3. Okay? That's the only regular polyhedron that cannot be packed on a 3 sphere. It needs to be packed on a three-dimensional hyperbolic space. And very recently, Nan studied this packing, and we find that this packing is actually, it can be fully packed in hyperbolic space, and we can flatten this structure back to flat space. And if the structure is small, we have a disk-like geometry. If the structure becomes larger, and it will wrap up and spontaneously break the rotational symmetry and form this burrito-like structure. Okay, so this is actually one example demonstrating the potential usefulness of curved space lattices. And by going to curved space and form a lattice, it can help us understand some interesting physics in our flat space. Okay, and now let me switch gear, talk about 2 dimensions. Let's study 2D periodic lattice in curved space, in 2D curved space. Okay, and here we want to consider uniform 2D space. Uniform means every single point has the same curvature, so we have 2D surfaces with constant curvature. If we want the constant curvature, the 2D manifold can only have 3 possibilities: constant curvature 0, constant positive curvature, constant negative curvature. If it's constant curvature 0, then this is basically flat space. If we want to form a lattice in flat space, in 2D flat space, we know that there are only 5 possible Bravais lattice we can have. That's shown here. And this Bravais lattice can only support 4 possible point groups and 17 possible space groups, also known as a wallpaper group. Okay? So for flat space, we have only a finite number of lattices we can construct, and they are well understood. If we have a positive constant curvature, basically a sphere, And the situation is also very well understood. If we want to put a lattice on a sphere, there are only a finite number of situations we can have. Basically, what we are doing here is to making regular polyhedrons on a sphere. And these regular polyhedrons, we only have 5 of them, and their symmetry group is some subgroup of the SO3 rotational symmetry. The situation that we have the minimum understanding, we have this amount of knowledge is a hyperbolic surface. If we have a constant negative curvature, then this 2D surface is a hyperbolic surface. Hyperbolic surface is very different from a sphere. Sphere has a finite size, but hyperbolic surface has infinite size. More importantly, if we have a hyperbolic surface and we try to draw a periodic lattice on hyperbolic surface, there are many different lattices we can draw. And these lattices have very different symmetry and the infinite many classes we can have. That's very different from positive curvature and flat space. Okay, how do we construct such a lattice, or what does a periodic lattice on a hyperbolic surface looks like? So here, let me first introduce a terminology about this PQ tiling. So the periodic lattice in curved space and hyperbolic space can be often labeled by 2 integers, P and Q. Okay, so P and Q are 2 integers. Let me clear this a little bit. Sorry. Oops. I don't. Okay, let me do this. Okay, I can't clear it, but it's okay. So it's defined by 2 integers, P and Q. So P actually tells us the number of edges of each polygon. Okay, so here is the figure down below shows a so-called 7-3 tiling. The first number 7 tells us, this polygon we use have 7 edges. Each of them have 7 edges. Okay, and the second integer Q, this 3, tells us that at each corner, how many polygons meet together at each corner. 3 means at each corner, 3 polygons meet together. Okay, so here is a periodic lattice on curved space, on hyperbolic lattice. Okay, all the polygons are exactly identical, and all the corner points are identical. In this figure, it may look like the polygon in the center is larger and the polygon near the edge is smaller. This is because we project this curved space, the hyperbolic space, into a flat disk using the so-called Poincare disk model. If we really go back to the curved space, all the polygons will be the same and all the corners will be the same. So bottom line, periodic lattice for hyperbolic lattices, we can often describe it using 2 integers, a number of edges for each polygon and the number of polygons at each corner points. That's P and Q. Okay. And for experimental realization, of course, if we want to realize such a lattice, one way to do it is really use a hyperbolic surface. And that turns out to be very complicated. And an easier way to realize these experiments is to realize the connectivity, but not really the curvature. So if we have a tight binding model, if you think about tight binding model don't really care about the location of the points. It only care about the connectivity of the lattice. So in experimental realization, most of the experimental realization of hyperbolic lattice nowadays are using a flat space and just try to repeat this connectivity instead of really repeating this curvature. As long as we have the right connectivity and consider tight binding model, it's the same curved space lattice. Okay, and this curved space lattices in hyperbolic curved space lattice have some interesting phenomena, interesting property. For example, this 7-3 tiling I showed early on, the center of each plaquette is a 7-fold rotational center. And this 7-fold rotation is actually beyond what one can achieve in flat space. In flat space, we know the lattices can only give us 2-fold, 3-fold, 4-fold, or 6-fold rotational symmetry centers. We can't get any other number beyond this 4. But in a hyperbolic lattice, there are infinite many possibilities. Basically, any rotational symmetry we can imagine, we can find some lattice which gives us this rotational symmetry. Another interesting and special property about hyperbolic lattices is the number of unit cells. Okay, if we make this lattice bigger and bigger, L is the linear size of the lattice. If we increase the size of L, for flat space, the number of unit cells scales as L to power D. D is the spatial dimension. Okay, but in hyperbolic lattice, the number of unit cells increase exponentially, and it is much faster than any finite dimensional real space, flat space. Okay. And on top of that, this actually a unit cell counting actually leads one interesting consequence about connection between bulk and edges. In the thermodynamic limit, when L is very, very large, we know that for flat space, most of unit cells are in the bulk, and only a small number of unit cells are on the edge. The fraction of unit cells on the edge is much smaller than the bulk in the thermodynamic limit. So in other words, in flat space, this is the reason why in flat space, usually we say in small dynamic limits, boundary condition usually doesn't matter. Unless it's some topological state, most of the cases, boundary condition doesn't matter. Whatever boundary condition we use, we'll get the same conclusion. It's because boundary condition only have a small influence on the system because only a small number of unit cells are on the boundary. But for hyperbolic lattice, this is not the case because the unit cell number increases exponentially if we count the number of unit cells in the bulk, and on the edge, their number are roughly the same, comparable with each other. Okay, and how do we generate such a curved space lattice? Well, the trick is actually very easy. The technique is very easy. We use infinity mirror. Okay, so if we have two parallel mirrors facing each other, then the mirror image between these two mirrors will give us infinite lattice, infinite 1D lattice, as shown in this picture. Okay, and we can do a more complicated construction. We can use 3 mirrors and form a triangle. If we have 3 mirrors form a triangle, what we get is a kaleidoscope. And we know kaleidoscope will give us all kinds of fancy and beautiful pictures, and it's commonly used as a toy. But if we design this shape of this triangle to be, some properly designed shapes, then this kaleidoscope can give us a periodic lattice in flat space. For example, triangle lattice or honeycomb lattice, as shown here. Okay, in curved space, we can get curved space lattice using exactly the same construction, using 3 mirrors form a triangle. So on the on the right hand side, we can use 3 mirrors to form a small triangle, and we put the 3 mirrors on the edge of any one of this triangle, either the blue triangle or the white triangle. And then the mirror image among these 3 mirrors will generate this pattern. And this pattern is exactly the same as the 7th retelling I showed on the left-hand side. This is how the periodic lattice is generated for curved space. Start from 3 mirrors, and then let this mirror repeat again and again. Okay. So if these starting mirrors are called sigma 1, 2, 3, these are the 3 starting mirrors, then any combination of these 3 mirrors is also a symmetry operation in this lattice. And all the combination of these mirrors give us a group. That's our symmetry group. And this group is called a Coxeter group. And this Coxeter group serves the role of a space group of a lattice. It contains translations, rotations, reflections, and the combination of these 3 ingredients. Okay. That's the space symmetry of a curved space lattice. Okay, so we know how to generate this lattice now, and then we can ask one more question. If we have such a lattice, and we have particles or waves moving on such a lattice, how do we characterize the motion of particles or waves or modes on that lattice? Well, before we answer this question, let's first look at the flat space. Okay, so for flat space, we know what to do. If we have flat space continuum and homogeneous flat space continuum, we know the eigenstates are plane waves, and the eigenenergy is a function of wave vector k. If we have periodic lattice, the story is very similar. Just we replace plane waves with Bloch waves, and then the eigenenergy become a band structure, and n it gives us n is the integer labels different bands. Okay, and in flat space, we know we need to use Bloch waves. Okay, but why do we use Bloch waves to describe particles moving in a lattice? It turns out the answer is the fundamental answer comes from symmetry and the symmetry representation of the symmetry group. Okay, so in order to explain this, we need some basic knowledge, about the representation theory of a group. So for students in the audience who may not be familiar with the topic, here I will do a very quick review to review the basic concept about the representation of a group. And here, instead of giving a rigorous proof and a mathematical presentation, I will try to do a simple demonstration using quantum mechanics as an example to demonstrate the flavor and the basic meaning of this terminology. Okay, so let's start from a Hilbert space, and this Hilbert space has a bunch of quantum states psi. And the symmetry operation of this quantum system forms a group. And if G1 is a symmetry operation, G2 is a symmetry operation, then the multiplication of G1 and G2 is also a symmetry operation. And the multiplication means we first do G1, then we do G2. Okay. And under some symmetry operation, quantum wave function psi will become psi prime. We know in Hilbert space, wave functions are normalized. If wave functions are normalized, then this psi and the psi prime must be related with either a unitary or anti-unitary matrix. And here, let's only consider unitary symmetry. So we'll assume this U is a unitary matrix. And this unitary matrix is actually a way to represent this symmetry operation. And that is called a representation of the symmetry group. Okay, so basically for every single element of the group, we can map it to a unitary matrix, and this unitary matrix represents this symmetry group. Okay, and we can easily verify that this unitary matrices and the group element follow exactly the same production relation. The product actually defined exactly in the same way. Okay, and we can demonstrate this using some examples we are familiar with. For example, we consider central potential in quantum mechanics. In central potential, we know a system with central potential, we know the system has SO3 rotational symmetry, and the rotation form SO3 rotational group. And the rotation is, we can label them with R, so that is some rotation. And for quantum wave functions, this quantum wave function changes following a unitary operator or unitary matrix. This unitary operator or unitary matrix is actually exponential of the angular momentum operator. Okay. And this unitary operator and this unitary matrix is a representation of the SO3 rotational group. And this unitary operator is constructed by the angular momentum operator. It is actually a very large n by n dimensional matrix, and n is a dimension of the Hilbert space. Okay, so typically this is a very large dimension, typically infinite. And a very large matrix is very hard to handle, and we need to find some tricks to simplify the problem. Okay, so in quantum mechanics, this trick actually always works. If we have some complicated quantum mechanics problems, we can always try to find some good basis. Once we go to the good basis, then the problem is dramatically simplified and become much easier. Okay, turns out for the rotational symmetry case for central potential, we should do this to get the good basis. Okay, so we should try to find another good set of bases such that this good basis makes this rotational matrix into block diagonal matrices. Okay, that's what we want to do. Okay, so we want to choose a new set of bases such that this unitary matrix become block diagonal. And we want to block diagonal all the rotational matrix, not just diagonalizing one. We want all the rotational matrix to be block diagonal, and they follow the same block. And on top of that, we want each blocks to be as small as possible. We want to break this big matrix into small blocks. Okay, and it turns out we know what to do. The best basis we should use is this basis. R is some arbitrary function of radius, and this Y is spherical harmonics. Okay, under rotation, R doesn't change. Radius doesn't change. The only thing that changes under rotation is spherical harmonics. Okay, and if we use spherical harmonics as our basis, then the rotational matrix become block diagonal. We have 1 by 1 block, 3 by 3 block, 5 by 5 block, etc. This 1 by 1 block is formed by S-wave states, because S-wave state does not change under rotation. So we just multiply it with 1, and that's why it's a 1 by 1 matrix of unity. 3 by 3 matrix come from P-wave states. P-wave state has 3 states. M equals -1, 0, +1. M is LZ quantum number. And these 3 states evolve into each other if we do a rotation, and that gives us a 3 by 3 block. And angular momentum 2 give us a D-wave state, give us 5 by 5 block, etc. Angular momentum L give us 12 by 12 blocks. Okay, and because these blocks cannot be further reduced, cannot be made smaller, each of this block is called a irreducible representation of the rotational group, or IRIP. Okay, irreducible here means we already block diagonalize the structure, and we cannot further, block diagonalize this structure to make it smaller. Irreducible means it cannot be further made smaller. Okay, and for the rotational group, irreducible representation are labeled by the angular momentum quantum number L. Each value of L gives us 1 representation, and the dimension of this representation is 2L plus 1. It means that we need 2L plus 1 quantum state to form this block, to support this block. And this 2L plus 1 state are labeled using the LZ quantum number M. Okay, so that's a irreducible representation. And we know that for rotational invariant systems, for central potential, this is indeed a very good basis. Okay, and it turns out this principle is universal. For any symmetry group, it works the same way. For any system, for any quantum system with some symmetry, we should always use reducible representation of the corresponding symmetry group to organize our basis. If we do that, the problem will get dramatically simplified. And this is because IRIP has a bunch of good properties. First of all, IRIP makes the matrices into block diagonal matrices. It means that we simplify a very complicated, huge matrix problem into a bunch smaller matrix problem. We make a complicated problem into a set of smaller, much easier problems. And more importantly, this irreducible representation gives us good quantum numbers. So the number, the quantity we use to label different irreducible representations is actually our conserved quantity or good quantum number. For example, the rotation case, we use angular momentum to label different irreducible representations. That is our good quantum number. Okay, and using this good quantum number, we can also block diagonalize Hamiltonian. Hamiltonian cannot mix two states from different irreducible representation. If we start from the quantum state in one irreducible representation, then the time evolution will always stay in this irreducible representation, cannot go to another irreducible representation. In other words, Hamiltonian is block diagonal. And Hamiltonian is block diagonal. It means that if we want to find eigenstate, it's become much easier. We can do that diagonalization for each small blocks at one time instead of diagonalizing a huge Hamiltonian. Okay. Another very important property of irreducible representation is it tells us the degeneracy level of quantum states, of energy levels, degeneracy of quantum level. Okay, so in quantum mechanics, sometimes we have accidental degeneracy. Those are usually not so important because if we do some small perturbation, they'll be gone. The more useful one are the so-called protected degeneracy. It means no matter how we tune the parameter, the degeneracy stays there. In quantum mechanics, there are many ways to get protected degeneracy. One common way is to get protected degeneracy using symmetry. And if the degeneracy is protected by symmetry, then the degeneracy level can be easily obtained looking at the irreducible representation. If we have a d-dimensional irreducible representation, it means that this state should have default degeneracy. So the dimension of irreducible representation also tells us the degeneracy level of quantum states. Okay, so for example, for central potential, we know the degeneracy level is 2L plus 1. Because the angular momentum L gives us 12 plus 1 dimensional representation. And for most central potential, it indeed follows this counting, with a couple exceptions. For example, hydrogen atom do not follow this. Hydrogen atom has a much higher degeneracy level, and it's because hydrogen atom actually has a higher hidden symmetry, SO4, instead of SO3. Okay, so bottom line, we should use irreducible representations to organize our Hilbert space to choose our basis. And this is a highly universal principle. And another interesting property of irreducible representation is that it does not depend on microscopic details at all. It only depends on the algebra of the symmetry. As long as we know the symmetry, we know the irreps. And different systems have follow the same, as long as they follow the same symmetry, they will have the same irreducible representation. Different physics system just gives you different combination of this irreducible representation. So this irreducible representation is highly universal. And this is part of the reason why no matter we have classical or quantum problems, at the end of the day, we use spherical harmonics for rotational invariant systems. It's because this irreducible representation does not depend on detail. It only cares about the symmetry. Okay, so now let's go back to Bloch waves. Okay. It turns out the reason Bloch waves are so useful in lattices is because Bloch waves are irreducible representations. More precisely, Bloch waves are irreducible representations of the so-called lattice translation group or lattice translation group. Okay, and so let's look at translation. So in continuum, we know that the continuum translation form a group, and that group actually has irreducible representations. And those irreducible representations are labeled by a good quantum number. That's a linear momentum quantum number, K. Okay, so if we have plane wave and we do translation, we get this factor in front. This factor is a 1-by-1 matrix, and it means that plane waves gives us 1D irreducible representation for translation. Okay, and for flat space translation group, the representation is irreducible representation is always one-dimensional. This is because in flat space, translation are abelian. Abelian means the group elements, we can switch the order, nothing happens. For matrix product, in general, matrix product are not abelian. In order to make sure that this representation is also abelian, follow the same, abelian structure of the translation group, we have to use 1-by-1 matrix. 1-by-1 matrix are the only matrices that guaranteed to be abelian. So this is the reason why translation group in flat space always has 1D representation. It's always 1-by-1 matrix. Okay. If we have a lattice, the story is more or less the same. The only difference is that the translation now cannot be an arbitrary real number. It needs to be an integer times lattice constant. We have only discrete translation. If we compare the lattice translation and the continuum translation, they are very similar, but there's one fundamental difference. That's this label of irreducible representation K. Okay. For continuum space, this k is linear momentum. It can take any real value. For a lattice, this k is the crystal momentum. It can only take a value between minus pi over a and plus pi over a. In other words, this k can only be in the first Boolean zone. The reason this k can only be in the first Boolean zone is because if we increase k by 2 pi over a, this phase factor doesn't change. Okay, 2 pi over a increased by 2 pi over a, this translation gives us a 2 pi phase increase. And 2 pi phase increase doesn't do anything. So in other words, k and k plus 2 pi over a are the same representation. So k can only be defined modulo 2 pi over a. Okay, because k and k plus 2 pi over a belongs to the same irreducible representation, it means that our Hamiltonian can mix states of k and k plus 2 pi over a, k plus 4 pi over a, etc. That means the eigenstates will be a superposition of k plus integer times 2 pi over a. If we write down the superposition of k plus 2 pi over, 2 times integer pi over a, then this combination gives us Bloch waves. That's the reason why Bloch waves emerge as a good basis for lattices. The fundamental reason is because these are the irreducible representations of our translation symmetry group. Okay, so now let's look at curve space. Okay, so for flat space, we know that Bloch theorem comes from irreducible representation of translation group. In curve space, before we can define Bloch theorem, we need to first define what is the translation group for curve space. Okay, and for curve space, we mentioned earlier on, we know the Coxeter group. We start from 3 mirrors, and then all the combination of these 3 mirrors give us a huge infinite group, and that infinite group is Coxeter group. Coxeter group actually serves as a full space group. It includes translation, rotation, reflection. We have everything. Okay, so the first step is to find the so-called translation group. So we need to find some subset of the Coxeter group that only give us translations, not rotations and reflections. Okay, so the first step, we need to find a subset that only contains translations. That's the first task. Okay, how do we do that? How do we find the subset that gives us only translations? Well, before we look at the curve space, let's take a quick look at the flat space again. In flat space, if we have the full spatial symmetry, translation, rotation, reflection, and all their combinations, then we can easily find the subset of translations. Okay, so we find the subset which we call the lattice translations. In order to do that, in flat space, it's extremely easy. We just find all the translations. Okay, and in flat space, this can be extremely easily achieved by holding one vector in my hand, and then I do a symmetry operation. Okay, if I find that after my symmetry operation, this vector always maintains its orientation, then I know this is the translation. It cannot contain any rotation, cannot contain any reflection. If I find that this vector changes its orientation, then it means that this operation contains some component of rotation or some component of reflection. So by requiring that the vectors never change direction, we can find a subset. And this subset are only composed of lattice translation, and that's our translation group. For flat space, this is extremely easy. But for curve space, the story is much tricky. The most complicated, the biggest problem is the following. In curve space, there's no clear boundary to distinguish translation and the combination of translation and rotation. Okay, so I can't really tell whether this operation is purely a translation or it's actually translation followed by a rotation. The reason is because this vector trick will not work anymore in curve space. In curve space, if I hold a vector and then I do a translation, and then this vector direction, the orientation of this vector will change. In fact, if I form a closed loop, do a translation around the closed loop, and go back to my original position, this vector will rotate to a different direction. And the angle between my final vector and the initial vector is actually, it measures the total Gaussian curvature inside this loop. So I can't use the orientation of the vector to decide whether it's a rotation or rotation combined with, whether it's a translation or translation combined with rotation. Okay, so simple intuition doesn't work. We need something more rigorous. We need to develop something more rigorous. And this development needs to be rigorously based on math and more precisely based on algebra. Okay, and that is actually the first thing we need to do. Okay, so before I show you how to find this translations and translation subgroups, let's first look at the flat space one more time. Okay, let's first look at in flat space. We know it's easy to obtain this translation subgroup. And what is a property? Let's try to first look at the key property of this translation group in flat space. Okay, in flat space, we can select translation very easily, and all this translation gives me a subset. And this subset has three key properties. First property, this subset only contains rotation. Only contains translation. It's a translation subgroup. It does not contain rotation, does not contain reflection, and does not contain the combination of translation and rotation, or translation and reflection. Okay, it's only contain translation. Second important property, this subset, it forms a group. It forms a subgroup of the space group. So it basically means all these elements, we can use their product to define a group, and this translation form a group. And this group is called the lattice translation group or lattice translation subgroup. It's a subgroup of the space group. Okay. Third property, and this property is usually not emphasized in textbooks, but it's actually a hidden property of lattice translation group. It turns out to be very important. This lattice translation subgroup has a one-to-one correspondence between group elements of this translation group and the unit cells of the Bravas lattice. Okay? To see this one-to-one correspondence, let's first choose arbitrary unit cell. Let's choose one unit cell. And let's put the origin of my coordinate into this unit cell. So this unit cell, I will call it unit cell and origin. Okay? If we start from this unit cell and origin, then we can get any other unit cell through a lattice translation. For example, if we want to get a unit cell at location n times a1 plus m times a2, n1, n2, a1, a2 are the two lattice vectors, two primary lattice vectors. If we want to get a unit cell at this location, then I can start from my unit cell at origin and then do a translation. Translate along the a1 axis n times, then translate along the a2 axis m times, and I get that new unit cell. So the left-hand side of this equation is a unit cell. It's a unit cell. The right-hand side of this equation is a translation. And this equation actually defines a one-to-one mapping between unit cell and translation, and this is a one-to-one correspondence. Every unit cell can be achieved by one translation and only one translation, and this is this one-to-one correspondence. As I mentioned earlier on, this is the important property of lattice translation group. It's not emphasized much in textbooks, but it turns out that it's a very important ingredient we have to keep. Okay, now let's go to the curve space. In curve space, ingredient 1, we cannot keep it anymore. It's because, as we mentioned earlier on, in curve space, we can't distinguish translation and the combination of translation and rotation. Both of them, vectors will change its orientation, so we can't distinguish them. This means that we can't keep this first criterion, the first property. We need to either abandon it or loosen this constraint. Okay? And luckily enough, if our goal is to define Bloch waves, it turns out we only need property 2 and 3. Property 1 happens to be the case for flat space, but it's actually not essential at all in terms of Bloch waves. Since for ingredient 1 need to be either rejected or loosened, and it's actually not important at all for Bloch waves, why not we just totally abandon it? Just use the last 2 ingredients as our definition of curve space translation group. Okay, so basically for curve space lattice, we have Coxeter group, which include translation, rotation, reflections, and all their combinations. And then what we need to do here is we need to find a subgroup of this Coxeter group. It is a subgroup. And this subgroup, the elements of this subgroup has a one-to-one correspondence between the element of this group and the unit cell Bravas lattice, just similar to the flat space lattices. And that is actually our definition for translation subgroups. Okay? And for a curve space lattice, we can try to find such a group, such a subgroup. If we could find such a subgroup, then we say this curve space lattice is a Bravas lattice, or more precisely, the generalized Bravas lattice. Okay, and this subgroup we find is a lattice translation group, or generalized lattice translation group for this curve space Bravas lattice. But there are some situations where this tiling do not allow us to find such a subgroup. If we cannot find such a subgroup, then this lattice, we call it not a Bravas lattice. If it's not a Bravas lattice, we can't define lattice translation, and thus we can't define Bloch waves. Okay, and Bloch waves can only be done for the first category. And if we have a curved space lattice, how do we know whether we could define Bloch waves or not? How do we know it belongs to the first category or second category? Well, it turns out it's very easy. We can just use this sufficient and necessary condition. As we mentioned earlier on, the curved space lattices are labeled by two integers, p and q. P tells me how many sides each plaquette has. Q tells me how many plaquettes meet at each corner. Okay, the criteria is very simple. We look at this integer q and find its primary divisor. If we have one primary divisor and its number is smaller than p, then we can find the subgroup. It is a Bravais lattice, and we can define Bloch waves. If we cannot find a primary divisor smaller than p, then we can't do it. So that's a sufficient and necessary condition. Okay, so here I demonstrate one example of 14-7 tiling. 14-7 tiling means each plaquette has 14 edges, and that's plaquette showing on the figure on the left-hand side. And for each corner, we have 7 of these plaquettes meet together. This is 14-7 tiling. Our Q is 7. 7 has a prime divisor, which is 7. Okay, 7 can be divided by 7. And 7 is smaller than 14. It satisfies a sufficient and necessary condition, which means this lattice is a Bravais lattice, and we can define translation group, and we can define Bloch waves. And the translation group here is generalized, is shown on the figure on the right-hand side. So right-hand side, I showed one plaquette. Using this one plaquette, we can get 7 translations. Translation gamma 1 moves edge 1 to 1 prime. Translation gamma 2 moves 2 to edge 2 to 2 prime, etc. We have 7 translations. And these 7 translations are our generators, and we use their combinations, and any combination of these 7 translations give us some other translation, and they form a group. And this group is a non-abelian group. As you can see here, gamma 1 times gamma 2 and gamma 2 times gamma 1 gives a totally different translation, very different from flat space. And this translation group has one-to-one correspondence between its group element and the unit cells. That's very nice, exactly what we need. And it follows some constraints, it obeys some constraint. And one can prove that this translation group is isomorphic to the fundamental group of 3 torus. Okay? So this is something one can rigorously prove. And this non-abelian group has actually infinite many representations. It has infinite many 1D representation, infinite many 2D representation, infinite many D-dimensional representation, and this D can go up to infinite values. Okay, since we have so many representations, how do we label these representations? Well, we just need to follow the same principle and same way we did in flat space lattices. In flat space, each K point in the Boolean zone gives us one representation. We use K point in the Boolean zone to label representations. And in curved space lattices, it's exactly the same story. We define some generalized Boolean zone, and this generalized Boolean zone, every single point in it gives us a representation. The only difference between flat and curved space is that in flat space, the dimension of Boolean zone is the same as dimension of the real space. For example, if we have 2D lattice, Boolean zone is the 2D area. But in curved space, that's not the case. In curved space, for example, for the 14-7 tiling we mentioned early on, the dimension of the Boolean zone follows this formula. G is 3 here. It's a genus. Okay, and as we can see that the dimension of the Boolean zone does not match the dimension of the real space. Real space, we have 2D real space, 2D hyperbolic lattice. But the dimension of Boolean zone actually increases very rapidly when the dimension of the representation D increases. Okay, so this is the reason why, in curved space lattices, although the lattice is 2D, it can realize physics of higher dimension. It can realize higher dimensional physics. It's because the Boolean zone has a very high dimensional, space. Okay, so we know that we can label the irreducible representations, and we know that in principle we can construct Bloch waves. But how do we use this irreducible representation to construct Bloch waves? And let's first look again at the flat space. Okay. In flat space, we know that there are 3 ways to define Bloch waves. The first way is to say Bloch waves is a 1D irreducible representation of translation. So under translation, it gets extra factor, and this factor is my representation. The second way is what we call the Bloch theorem. It has a periodic function u and times e to the ikr. The third way use Wanni function. Okay. So Wanni function is actually a local function. It's the local function defined for every single unit cell. Here, R labels unit cell. Each R labels a different unit cell. Okay. So for one unit cell, I can define a Wanni function phi 0, so this is a unit cell at origin. And then for all other unit cell, I can do a translation for phi 0 and translate this phi 0 to other unit cell. And that gives us one function in all other unit cells. And we define one function in one unit cell and use translation to get one function in other unit cells. And then we do a superposition of this one function. And the coefficient of this superposition is e to the ikr. And then we get Bloch waves. These three ways to define Bloch waves are totally equivalent in flat space. And it turns out that for curve space, it turns out the first and the last definition are the most easy to use, and as we will show slightly later. Here I will highlight one thing before we go to the next slides, that is this exponential factor. If we compare these two exponential factors, we notice that these two exponential factors are inverse of each other. They have opposite sign. So the exponential factor we used in the definition of the representation, and the exponential factor we use in the definition of Bloch waves using 1D functions are inverse of each other. We will see that the same structure is actually true for curve space slightly later. Okay, now let's try to construct curve space Bloch waves. Let's start from one unit cell. Okay, let's say in one unit cell we have n degree of freedom. And this n could be a finite number if we have tight binding model. It could be infinite if we have continuum model. And because each unit cell has n degree of freedom, if we look at one unit cell, say let's look at one unit cell at the origin, then we can use n linear states as my basis to span this n-dimensional Hilbert space. Okay, so this is my basis for one unit cell. If I know the basis of one unit cell, then I can easily construct the basis of other unit cells through translation. And thanks to the one-to-one correspondence between unit cell and the translation. I start from my unit cell and origin, and I know its basis. And for another unit cell and R, I can find the corresponding translation and use that translation to translate my unit cell, origin unit cell basis into that unit cell. Using this translation, I get the basis of that unit cell. Okay, and I will label that unit cell and this. TR labels different unit cells. V gives the degree of freedom inside these unit cells. Okay, and since we have a complete basis, we can actually define any wave function using this basis. Okay, and but as we mentioned earlier on, this arbitrary state is not the most useful state. The most convenient state is actually Bloch wave state. And to get a Bloch wave state, we want to say some irreducible representation. Okay? And this is a d-dimensional irreducible representation of the translation group. Okay, if we know a d-dimensional representation of a translation group, then it means that we have d quantum states, psi 1, 2, 3, 4, all the way to psi d. And under translation, this d state actually evolve into each other, follow this matrix. Okay, and this is a definition of irreducible representation. And from this definition of irreducible representation, we can immediately write down the Bloch wave function. Okay, and let me explain this Bloch wave function a little bit. For arbitrary states, I need to give a coefficient for every degree of freedom in every single unit cell. But for Bloch wave state, we don't need to do that. For Bloch wave state, we only need to give the coefficient for one unit cell. And the coefficient in other unit cell are obtained through translation. Okay, so this construction greatly reduces the degree of freedom. I don't need to know the whole lattice. I only need to know what happened in one unit cell, and then I can use this translation representation to translate this unit cell into all other lattices. And due to time constraint, I will not prove this rigorous. I will not show you the rigorous proof this is a Bloch wave, but I will show you a hand waving proof by comparing this with with flat space. In flat space, we know we can use 1D functions to construct Bloch waves. Here is the same story. This object is our 1D function. Okay, and if we compare in flat space, if we compare the 1D function and the reducible representation, we find that this e to the ikr and minus ikr are inverse of each other. Here in curve space, it's exactly the same. One side we use rho, the other side we use the inverse of rho, inverse of the matrix. So the bottom line, as long as we have this one-to-one correspondence, the Bloch waves in curve space and flat space are exactly the same. The only thing we need to change is e to the ikr. This 1D representation we need to replace with higher dimensional representation with a matrix, and everything else remains the same. Okay? And once we have this quantum state defined, we can solve the eigenstate and for its eigenvalues for these Bloch waves. And I will skip the detail. And the key insight is here, if we use a Bloch wave state, we don't need to know the whole unit cell. Sorry, the whole lattice. We only need to know one unit cell. And what happened on other unit cell can be obtained through the translation. Okay, and that greatly reduces the complication of the problem. Instead of infinite system, I only need to solve one unit cell. Okay, and in this one unit cell, this Hamiltonian matrix greatly reduced. It's n times d times n. It's nd by nd. N is the number of degree of freedom. D is the number of the dimension of the representations. Due to time constraint, I will skip the detail. The basic story is the same. We have band structure in Brillouin zone. The only difference is how many bands we have. In flat space, the number of bands match the number of degree of freedom per unit cell. But in curved space, that's not the case. The number of bands is number of degree of freedom per unit cell times the dimension of irreducible representation. And we have this many of bands. We have more bands if you go to higher dimensional irreducible representation. And each band is actually default degenerate. It's because, as we mentioned earlier on, d-dimensional representation means default degeneracy. So we count degeneracy, the number of bands is number of degree of freedom per unit cell times d squared, times the representation squared. And here is one example. We demonstrated we calculate to demonstrate this principle. Here, basically, we put one atom in this in each unit cell of this 14-7 lattice, and then we connect this atom has this red dot, and we connect this red dot with springs. Okay, and we calculate the vibrational mode. And this dot can move in this 2D plane. It has 2 degrees of freedom for each dot, moving along x, moving along y. So I have 2 degrees of freedom per unit cell. In flat space, if you have 2 degrees of freedom per unit cell, we have 2 bands. That's exactly what happened if we use 1D representation in this curved space. 2 degrees of freedom, 2 bands per unit cell. But if we compute the band structure for 2D irreducible representation, we find the number double. And number doubled is because we are doing 2D reducible representation, and number of bands is degree of freedom times d. D is 2 here. And each of this band is 2-fold degenerate because I have a 2D representation. So the total number of bands is actually 8 if we go to 2D representations. Okay, so I think I'm running out of time, so I will skip the detailed discussion about the last section. So basically, in this last section, we were looking at the edge state. And it doesn't matter where does this edge state comes from. It could be a topological edge state or from, like, say, non-Hermitian skin effect, etc. As long as we have edge state, we can study how this the amplitude of this edge state decays into 0 when we go deeper and deeper into the bulk. Okay, and this decay we are looking at is not decay near the edge; it's decay deep into the bulk. If we are looking at the state deep into the bulk, far away from the edge, then what we are looking at is unit cell far away from edge. It's a bulk unit cell. And the mode there follow the same equation of motion as bulk cells. So it follows, so the bulk translation symmetry actually can tell us something. The rigorous mathematical construction was developed by Donghai Li and coworkers in the early 80s. So this so-called transfer matrix technique, it can be used to rigorously construct the decay of this edge state for any type of edge states. And the bottom line from this construction is that if we go into the bulk, the decay of this edge mode is described by a complex K. Okay. A complex K basically means this irreducible representation become non-unitary. It's not the unit, the Hermitian conjugate multiply itself is not 1 anymore. And in flat space, actually, it's well known that the unitary representation gives us bulk mode, and the non-unitary representation, superposition of non-unitary representation gives us edge mode. But for curved space, that's not the case. For curved space, unitary representations are bulk, that's no problem. But for non-unitary representation, it depends on the dimension of the representation. One can prove that 1D representation can never give you edge state. It can only give you a corner or bulk state. And the reason is because curved space translation is non-abelian. If it's non-abelian, then we can define a commutator. Commutator is defined this way. For abelian group, the commutator is always trivial, just identity. But for non-abelian group, this commutator is non-trivial. And if I have 1D representation, this commutator is mapped to 1. It means that this translation along this edge, along this direction, the wave do not decay. It always goes back to the same amplitude. And in the 14-7 tiling here, we demonstrate one example in the 14-7 tiling, where if we follow this blue direction, we can see this mode does not decay. It's oscillate. It's because along this direction we have one of these commutators. And because the group has infinite many commutators, we have many directions where the mode does not decay. And because this mode does not decay in many different directions, it cannot be edge state. It can either be a bulk state or a corner state, but it cannot be edge. Okay, I think I'm running out of time. So, and this is a good point to stop. And I will stop here. And thank you for your attention.
谢谢沈老师的报告啊，很精彩。然后接下去是提问的时间，这个大家有什么问题，无论是线下还是线上的，都可以随便提问。
我提个问题。
好的，
吴老师您说。
你好。
你好，你好，
好久不见。
对对对，你好，是好久不见，是。
我提个问题就是，在这个 flat geometry 的 case 的话，我们通常比方说画一个lattice， 我们这两个 lattice 点之间的 edge 都用一个直线来表达。
对的，是的。
在这个 curve 的 space 的时候，应该用这个短程线来代替，对吧？
是的，是的，是的。对，是这些线其实是 geodesics。
对，你这儿画的都是 geodesic，right？ Yeah。
对对对对，是的，是的，是的，是的，是的。
就是
因为它那个投影在二维平面里面看着是个曲线，其实它是直线 geodesic。
对对对，所以我注意到你刚才这个画二维的时候，有一个这个红的，那是第几页啊？有一个红的这个图，里头是7个边儿。
对对对对对。
那个边儿，我觉得你画的好像都是直的，是不是？你都画的直线。
那个sorry， 我忘了 label 了。那个图是从那个 Wikipedia 上考上来的，那个图是画成直线。
对，
那张图应该只是在 demonstrate 它的 connectivity， 它并不是真正的那个 geodesic。
就是更准确一点，要有这个平移不变性的话，实际上应该是
应该是这个图是我们自己画的，应该是这样的。对对对对
，OK，
that's a good point。对对，是那个图是我偷懒了，我直接从 Wikipedia 上 copy 下来，我没有仔细用正确的 geodesic 图画那个图。
这是头一个问题啊。第二个问题的话，就是这个 lattice， 假如一个 unit cell 里头有包含一些这个其他的 particle。
对对对。
所以就是像在 flat lattice 的话，你这个所谓的 wave phonon 实际上是可能有那什么，这些问题你讨论过吗
？sorry， 就是有就是每个 unit cell 超过一个 set。
对对
对，会有 optical phonon。
对对对，
是的。是的，是的，那就是这个和 flat space 一样，如果每个 unit cell 超过一个 particle 的话，是会出 optical phonon。
对，但是在解这些 phonon mode 的时候，
对，
是不是会比这平的 lattice 会复杂一点？
是会更复杂，就是那个，就至少我们会有2维 representation、3维 representation， 这高维 representation 会给出更多的 band。
这些问题
其实在这个就是我们这个 principle 其实是在所有的那个就不管多少个 atom 都可以适用的，只是在这个 demonstrate 的时候，我们 demonstrate 了一个 example 是每个 unit cell 放了一个 atom， 所以在这个 construction 里面，我们是允许每个 unit cell 有 n 个 degree of freedom 的。
对，
在放一个这个 atom 的时候，其实就已经有一些新的现象，跟 flat space 不一样的现象了。比方说这里的这个右下角这个图，sorry 左下角这个图。左下角这个图其实是1D representation 一维表象的 band structure， 因为我们只有一个 atom per unit cell， 这个一维表象的这个 band structure 其实就是 acoustic band， 但这个 acoustic band 我们要仔细看的话，这个 acoustic band 的能量不到0。在 flat space 里面 acoustic band 的能量总会到0，因为 k 等于0的那个点是个 global 平移。
对对对。
对，但是在 curve space 里面不是这个样子。curve space 里面，即便我们看 acoustic band 它的那个能量其实也不到0。准确的说，这个 acoustic band 的1维表象、2维表象能量不到0，需要到3维表象能量才能到0，因为这 global translation 其实是在3维表象里出来，不在1维和2维表象里。
OK。
对，然后如果加了更多的 optical mode 的话，在上面会出更多的 mode， 那些 mode 能量就更不在0。
I see。
对
OK，
但是这个它
so,
那个是可以 handle 所有的 situation 的。
OK，good，我第二个问题就是分类做的怎么样？
对，
能做全吗？现在？
是 lattice 的分类吗？还是？
对，就是相当于这个lattice structure，
对
像
，lattice 分
point
类
group 或者
做不
space
全。
group 的推广。
对，这个做不全，因为这里面有 infinite many lattice，infinite many space group。在平时空间，我们是知道那个什么100多少3维100多少，那个2维是10来个，这个我们是知道的。但是在 hyperbolic lattice 是 infinite many。
对，
因为这里没有一个
整个
complete
group
classification。对
space group 在连续 continuum 的 case， 它有这个 infinite many
infinite many space group。是的。所以这里面没有一个 complete classification。
但是分类，我觉得似乎好像也许有可能，我不知道。虽然有无穷多个，但是分类不一定无穷多个。
对，各 Coxeter group 的分类是那个 mathematician 做过。有一些像那个像那个 SU2 那些羊图一样，可以画一些图来代表这些分类。但是这些图可以一直往下 construct 下去，可以有越来越多的不同的 space group。
OK， 第三个问题就是这个 complex case， 就相当于正曲率的 case。你这做的都是负曲率，所以它是无穷。
对，
正曲率的 case 结果怎么样？
正曲率其实就是在球面上，球面上只有有限的这种 case。其实球面上其实就是那个 regular polyhedron， 那其实只有5种。
对，
就是 tetrahedron、dodecahedron、octahedron、icosahedron、cube， 只有这5个。
但是像三维或者几维这个
that's good question。对，是3维的情况要复杂的多。是的。
不知道这些东西跟宇宙学会不会连上？
这个其实是个很好的问题。就是 in principle， 如果我们在 curve space， 比方说最后要写量子场论的时候，我们总需要一个 regularization。
对
，regulation 有各种各样的 introduce 办法，但真把它放在一个 lattice 上面的话，比方说做一个类似于 lattice QED 那样计算的话，那样的话就是一个自动的把 regulation 放在里面的办法。所以在我想象中 ，ultimately， 如果大家要想写一个量子的引力学的话，这个 lattice 很可能会在里面起一个很重要的作用，告诉我们怎么 regularize 这个 theory。
Okay，very good，thank you。
谢谢。
Very good job，very good talk。
谢谢吴老师这么认真的问题。其他同学跟老师，
我想问一个问题。
OK， 好，齐老板您说。
那个，我要问一下，
你好。
你好。如果是 flat space 的话，有一个我们可以把那个空间群磨掉 transition group， 得到一个 point group 的概念。在这个hyperbolic space 上。
对，that's a great question。至少不 generically 可以。在某些特殊的情况下可以，但是不 generically 是那个不一定能建出一个那个 point group 出来。
就一般来讲，那个 translation group 可能不是一个 normal subgroup。
是的。对，我们试图用 point group 做一些半 structure 的 further classification， 就是类似于 flat space 的，但是总是 run into 一些 trouble。这个好像不是，至少不是 universal 可以 construct 的。
孙老师，我可能有一个小问题，就是， 最近就是相当于有一些文章开始讨论，就是等于有一点绕过 band structure 这条路，就是在 hyperbolic 里面直接去算它的热力学极限的态密度。我不知道您的这个方法最后能和他们的结果能吻合吗？还是您觉得找无穷维的这个表示的话，永远是有一个尽头的？所以
这其实是个很好的问题。这个问题我们确实还没有想过，这确实是一个很好的问题。理论上说，用这个 high dimensional representation 去算所有的态密度，也许不是一个最好的办法，因为这个 representation 是有 infinite many 的，有1维、2维、3维，一直到无穷维。真的要想算态密度的话，理论上得要把所有的态都加进来，对吧？所有的 representation 都考虑进来，才能算总的态密度。这个 representation 其实干的一个有意义的事情是把这些 band split 成不同的 representation。
对。
但是如果我们只看同一个能量，想知道同一个能量不管 representation 有多少个态度的话，把它分成 representation 可能反而就不是一个好的办法了。那这样来的话，我们得把所有 representation 都算完了以后，才能知道有多少个态，这样可能就变得又更加 complicated 了。对于真的要是只看态密度的话，也许还是在 real space 看会更好一些，不经过这个 representation 的计算。
那基本上就完全用递归和定函数那一套去做。
对，我觉得我感觉应该是这样。这个问题我没有真的仔细考虑过，但是我觉得好像是这样。
然后还有另外一个非常细节的问题，您最后最后一行提到那个 pi one 就是 fundamental group， 为什么这个 three torus 可能我没太听懂。就是
对，就是这个 happens to be true for 这个对这个14期的 tiling， happens to be true。我看我能不能找到一个图，sorry， 这个用的是一个 pad， 所以这个图 slides 不是太好找。对，就这张图吧。
对，这
个14期的这个 tiling，如果我们从这个看这个图 B， 我们把1和1 prime 这两个 edge 格录在一起，2和2 prime 这个格录在一起，3和3 prime 格录在一起 ，etc. 把这每一个成对的这个edge 格录在一起，这个 unit cell 其实会变成一个 three torus。
OK， 就是按您这样显示的连接方式连在一起的。
对。这个在网上有一个很好看的 video， 我没有加在我的 slides 里面，就是这个一点一点粘起来以后能粘出一个 three torus 出来。
OK，
所以这些所有的这些 translation 其实是在 three torus 上画大圆。
OK， 好，谢谢你。
对，这一旦把它粘成一个 three torus 了，这些 translation 就都变成 three torus 上的 loop 了，也就是 three torus 上的 pi one。
OK。其他同学跟老师还有别的问题吗？随便提问，很好的机会。不是你上来问，你稍微等会儿，有个学生可能有个问题，他上来一下。你在对着麦克风。
老师，我有一个细节上的问题，就是这个题目里也有一个二维表示的能带，然后那个地方的二维表示的话是应该不是唯一的吧？应该可以，就是您当时有一个公式里面是可以，对，但是就是那一页那个二维表示的能带，您是
是的，我们的那张图里面画的是在二维表示的布里圆区里面 cut 了一条线。
对，但是就是我想问一下，就是这个 lambda 这个参数，就应该是可以选。我看了一下，有个公式是应该可以选，有好多个参数，你应该是选的其中一个。然后这个参数是怎么选的呢？
这个是随机选的，这个是我们就随便选了一个。这个其实和 flat space 一样。比方在 flat space 里面，我们真要画一个二维系统的 band structure， 这是一个3维，需要画一个3维的图。但真是画一个3维，或者我要想画一个3维系统的 band structure， 需要画一个4维的图。但真实情况下画不了4维的图，所以真实情况下干的事情就是在那个布里圆区里面切一条线，然后画这个沿着这条线的这个能量是怎么变化的。我们就是在这个二维表象的布里圆区里面随机的切了一条线。
那这个地方我就是想问一下，就是这个地方的参数应该就是变量的话有很多个，您这个是都能确定下来的吗？
就是整个便利二维的representation 是吗？
对对对，就是我
对这个按照我的理解，好像还是一个没有完全解决的数学问题。数学上知道二维 representation 的这个布里园区有多大，但是想要把它每一个 representation 都写出来，我好像还没有看到那个有这样的结果。
就是满足就是您的就是限制条件的这种二维的。
对，我们知道布里园区有多大，但真的要把这个布里园区里面的每一个点都写出来，其实并不容易。
OK，就是说，
我们知道应该怎么样构造这些二维 representation， 但是想要完全便利它，至少在我看到的 literature 里面，还没有一个真的是完全便利了这个二维的 representation。
好，谢谢老师。
对，但是这个 block theorem 的一个有趣之处就在于，你想算这个 eigenstate 或者 band structure 的时候，你并不需要知道所有的 representation， 只要你知道一个 representation， 你就可以知道这个一个 representation 里所有的 eigenenergy 了。对，所以我们还没有得到整个的 band structure， 但是如果我们知道我们想要算 band structure 的布里园区里面任意一个区域的任意一条线的 band structure 的话，都是可以用这个办法来算的。这个是很好的问题。这真的要是想便利整个二维的布里园区，至少在 curve space general 的 curve space lattice 里面，这还是一个没有解决的问题。
好的，谢谢老师。
好嘞。还有其他同学跟老师有什么问题吗？行，如果没有的话，我们今天到这里吧。这个最后再谢谢孙老师，很精彩的。
谢谢。
好，
谢谢。
好，谢谢。好，谢谢。
李老板要过来打个招呼。也是精彩。
好久不见，小峰。
好，下次邀请你来复旦。
好，一定。
对，下次我来坐。对。
好，谢谢。
拜。
好，拜拜。